the universe is not only expanding, it is accelerating. Galaxies moving away from each other faster than gravity should allow. A mysterious force, dark energy, permeates all space. It exerts pressure, negative pressure, pushing galaxies apart, as if the cosmos itself is stretching. Imagine space, a rubber sheet being pulled not from the edges, but from every point simultaneously. This is not a simple push. It is uniform, acting everywhere, in every direction. Einstein once introduced the cosmological constant, a term in his equations to counterbalance gravity. At the time, it seemed unnecessary, yet now it may represent the energy driving accelerated expansion. Some theorists imagine a uniform fluid filling all of space with energy that resists gravitational collapse. This dark energy is invisible and interacts weakly with matter and light. Yet its influence dominates the universe. Galaxies recede faster the farther away they are. This observation led to the discovery of cosmic acceleration. Changes everything about the universe's fate. Could expansion continue forever accelerating? If so, the big rip may occur. Structures, galaxies, stars, even atoms could be torn apart as space stretches infinitely. Alternatively, expansion may slow, stabilize, and the universe may reach equilibrium. The influence of dark energy also affects galaxy formation, the growth of clusters, the evolution of cosmic filaments, all subtly modified by this pervasive force. To study dark energy, astronomers rely on light, traveling billions of years. Distant supernovae, type I, serve as standard candles, measuring their brightness, and redshift reveals the expansion rate over cosmic time. Redshift, the stretching of light as space itself expands, provides a window into the velocity of galaxies. Large-scale surveys map galaxy clusters, the cosmic web. These structures trace the gravitational influence and reveal the push of dark energy. Cosmologists combine theoretical models and precise observations to constrain the properties of this invisible force. Some speculate dark energy may vary over time, or it may remain constant, a true cosmological constant. Understanding dark energy requires both imagination and careful observation It challenges our notions of physics, space, and time. This force represents over 2/3 of the total energy content of the universe, yet it is largely unknown. Its nature elusive, its origin mysterious, as galaxies drift. Their motion encodes the history of expansion and the influence of dark energy. The universe is a dynamic fabric, constantly shaped by unseen forces. Dark energy acts as the hidden architect behind accelerated expansion, altering the destiny of cosmic structures. Each observation, each measurement brings us closer to understanding this enigmatic force. Even tiny deviations in galaxy distributions or supernova brightness can hint of the physics of dark energy, the interplay between matter, gravity, and dark energy defines the cosmic landscape, the fate of everything within it. It is a vast, slow-motion dance. Oh, invisible pushes and gravitational pulls that stretches across billions of light years. Cosmology is our attempt to decode this grand design, to understand why the universe expands, why it accelerates, and what awaits in the far future. Dark energy continues to shape the universe. Its influence grows as space expands. Galaxies drift apart, their motion faster than expected from gravity alone. This acceleration affects the formation of cosmic structures. Clusters of galaxies cannot grow as efficiently if the space between them stretches too quickly. Filaments of the cosmic web thin and stretch under the pull of dark energy. Some regions may become isolated, cut off from neighboring structures. As expansion outpaces gravitational attraction over trillions of years, the universe could become a collection of lonely galaxies, each in a vast emptiness, with no other galaxies nearby. Alternatively, the expansion might slow if dark energy diminishes or transforms into a weaker form. This would allow gravitational forces to regain dominance and cosmic structures to form more robustly. The Big Rip scenario remains one of the most dramatic possibilities. All bound systems, stars, planets, even atomic structures could be torn apart as dark energy overwhelms gravity. However, observational data suggests more moderate expansion. The rate of acceleration may be constant or only slowly changing Regardless, dark energy reshapes the cosmic timeline. Studying distant supernovae helps measure expansion history. These standard candles emit predictable light, which dims with distance. Comparing observed brightness to expected brightness reveals how fast space has stretched. Over billions of years, redshift surveys map millions of galaxies to understand clustering patterns, how cosmic structures respond to the invisible push of dark energy. Large-scale structures like the Sloan Great Wall or the Hercules Corona Borealis Great Wall offer clues about how expansion and dark energy shape the universe. Even voids, enormous empty regions between filaments, reflect the influence of dark energy. The cosmological constant remains the simplest model of dark energy, yet alternatives exist. Quintessence, the dynamic field changing over time, could better explain subtle anomalies. Scientists also examine cosmic microwave background radiation. Its minute fluctuations contain imprints of early expansion and the influence of dark energy. Weak gravitational lensing distorts the light from distant galaxies, revealing mass distribution and the effect of dark energy on cosmic curvature. Simulations model billions of years of evolution with varying dark energy properties. They show how galaxy formation, cluster mergers, and cosmic web evolution depend sensitively on the nature of dark energy. Understanding this force is critical not only for predicting the universe's fate, but for grasping fundamental physics. Could dark energy interact with unknown particles or hidden dimensions? Some theorists suggest connections to vacuum energy or M-theory brains. Every new observation, every improved measurement tightens constraints and refines our understanding. The universe is a vast laboratory testing gravity, matter, the mysterious dark energy cross unimaginable distances. The future depends on its properties. Will galaxies drift apart, forever isolated, or will cosmic expansion slow, allowing structure formation to continue? Even star formation within galaxies may be influenced by the large-scale expansion. Dark energy shapes not just the fate of clusters, but the very environment in which stars, planets, and potentially life can merge. Astronomers seek to understand this invisible force through careful observation, measuring redshift of distant galaxies reveals how fast space expands. Type Ia supernovae act as cosmic beacons, their predictable luminosity serving as standard candles. By comparing observed brightness to distance, scientists chart the acceleration over billions of years. Large-scale surveys map millions of galaxies, tracing the cosmic web. The expansion of clusters, weak gravitational lensing, bends light subtly, providing a map of matter distribution and hints of dark energy's influence. Cosmic microwave background remembers the early universe. Tiny fluctuations encode information about expansion history and energy content. All these observations converge to paint a picture of a universe dominated by dark energy, yet its nature remains elusive. Is it constant, a cosmological constant, dynamic, changing over time, like a field flowing through space? Simulations help explore how galaxies form, how clusters merge under different dark energy models. They reveal how even subtle variations in this force affect large-scale structure and the fate of the cosmos. Cosmologists develop models testing theoretical possibilities against observations. Some propose connections to quantum vacuum energy or hidden dimensions, linking dark energy to fundamental physics beyond the standard model. The fate of the universe depends on these properties. If dark energy continues accelerating expansion, the Big Rip may occur, disrupting all structures from clusters down to atoms. If dark energy weakens, expansion may slow, allowing gravitational forces to stabilize structures. Cosmic evolution to continue. Regardless of the outcome, dark energy reshapes our understanding of space, time, and the ultimate destiny of all matter. It is a force unseen, yet omnipresent, driving galaxies apart, stretching the fabric of space and challenging our comprehension. Every observation, every new survey brings us closer to understanding this cosmic mystery. The universe is alive with unseen forces, expanding, evolving, shaped by the hidden hand of dark energy. It reminds us that reality extends beyond direct perception. Galaxies drift apart, cosmic filaments stretch, and the vast emptiness grows. Yet within this dynamic cosmos, life, stars, and planets emerge, woven into the fabric of space, against the backdrop of accelerating expansion. Dark energy is both a challenge and an invitation, a challenge to understand the fundamental forces that govern the cosmos, an invitation to explore the universe at its largest scales, to seek the origins and ultimate fate of all that exists. As observations improve, as telescopes grow more sensitive, we will continue to decode the cosmic acceleration, the secret of dark energy in the vast expanse of space. Dark energy stretches silently, slowly shaping the destiny of galaxies, clusters, the universe itself. The story of cosmic acceleration. Not complete, but with every discovery, we come closer to understanding the hidden force that drives the universe onward. The cosmos is alive, dynamic, and mysterious. Dark energy remains the greatest and most intriguing of its secrets. Rogue planets drift through the galaxy unattached to any star. They exist beyond the familiar orbits, the warm light of parent suns, some within planetary systems, then were ejected by gravitational encounters. Massive planets interacting with siblings or nearby stars can be flung into the void. Others are remnants of destroyed systems, survivors of stellar catastrophes or collisions that disrupted their home. Theorists also consider planets composed of exotic matter, perhaps dark matter clumps, or unusual quantum fields, dense enough to form a planetary body. These hidden worlds vary in size, from small rocky objects to gas giants larger than Jupiter. Without a star, they are cold at the surface, yet some may harbor internal heat generated by radioactive decay or leftover formation energy. Subsurface oceans beneath thick ice shells could persist for billions of years. Geothermal heat from the planet's core might maintain liquid water, drive potential chemistry. Some scientists speculate life could exist without sunlight, thriving in these hidden oceans, or sustained by chemical gradients. Detection is challenging. Microlensing occurs when a rogue planet passes in front of a distant star. Its gravity bends light, creating a temporary brightening that reveals the planet's presence. Infrared surveys search for the faint glow from internal heat. Even small temperature differences can be detected with sensitive instruments. The motions of nearby stars can also hint at invisible companions. A planet's gravitational pull can subtly perturb other objects, revealing a hidden mass. Rogue planets may number in the billions, weighing stars in some regions. They roam through interstellar space, sometimes crossing stellar neighborhoods or passing close to solar systems. Encounters with rogue planets could destabilize orbits, trigger comet showers, or even temporarily capture the planet into a new system. Though isolated, these worlds are part of cosmic evolution, remnants of dynamic gravitational interactions, and the violent histories of planetary systems. Each detection expands our understanding of planetary diversity and the extremes of planetary formation. The study of rogue planets reveals that planetary systems are not isolated. They are fluid, chaotic, and constantly reshaped by gravity. Even in darkness, without a sun, some planets may be habitable beneath ice or rock, powered by internal energy. The population of these lone worlds challenges conventional notions of where planets exist and how life might persist in the universe. Astronomers continue to refine techniques to find these hidden travelers. Future surveys may uncover thousands more, mapping the wandering population of interstellar planets. Rogue planets serve as laboratories for understanding extremes of planetary physics, composition, and the potential for life without a star. Some rogue planets may retain internal heat for billions of years. Radioactive decay within their cores produces energy that can maintain subsurface oceans. Geothermal vents could provide chemical energy, supporting life even without sunlight. In extreme cases, life might rely on exotic chemistry, using alternative solvents or energy from chemical gradients. Thick ice layers protect these oceans from the cold of interstellar space. Water remains liquid beneath kilometers of ice. Not no veers. If present, could trap heat and shield life from cosmic radiation. Some rogue planets might even have moons whose tidal interactions generate heat through flexing of the planetary interior. Detection methods must be subtle, precise. Micro-lensing events remain the primary tool where a rogue planet passes in front of a distant star. Its gravity bends light, causing a temporary brightening. The effect is rare and brief, lasting days or weeks, depending on the planet's mass and velocity. Infrared observations seek heat emitted from the planet itself. Even small thermal emissions can betray the presence of a lone world. Astronomers also examine perturbations in nearby stars or anomalies in asteroid belts that suggest unseen planetary masses. Simulations predict a vast population of rogue planets in the Milky Way alone. Estimates suggest hundreds of millions to billions of such worlds crossing interstellar space silently and invisibly. Some may pass close to the sun or enter the outer solar system, temporarily influencing comets or altering orbital dynamics. These encounters could provide opportunities for direct detection or even future exploration. Rogue planets challenge traditional concepts of habitable zones and planetary formation. They demonstrate that planets are not strictly tied to stars, and that life might emerge in unexpected ways, even in total darkness. The study of these worlds bridges planetary science, stellar dynamics, and astrobiology. By understanding rogue planets, we gain insight. The chaotic processes that sculpt planetary systems and the potential niches for life beyond the sun. Future missions may employ wide-field infrared telescopes capable of detecting hundreds of previously unseen planets roaming between stars. Gravitational microlensing surveys will expand our senses and refine models of planetary ejection mechanisms. With every new detection, our picture of the Milky Way evolves from a static collection of stars to a dynamic system populated by both anchored and wandering worlds. Rogue planets represent a vast, hidden population, illuminating the extremes of planetary formation, survival, and the possibilities for life in the universe. Rogue planets continue their silent journey through interstellar space. They are remnants, violent gravitational interactions, and chaotic planetary histories. Their presence reveals the dynamic nature of planetary systems, the forces shaping them. Some may carry hidden oceans or internal heat, enabling the possibility of life without a parent star. Detection remains challenging, but each discovery illuminates new aspects of the Milky Way's hidden population. Micro-lensing, infrared observation, and orbital perturbation analysis remain the key tools for revealing these silent travelers. The numbers are staggering. Millions, perhaps billions of such worlds traverse the galaxy, unseen yet influential on the dynamics of star clusters and the distribution of matter. Rogue planets sometimes pass near stars or into planetary systems, momentarily altering orbits or stirring comets and asteroids. They provide natural laboratories to study planetary physics under extreme isolation. They challenge traditional views of what constitutes a planetary system and redefine habitable zones beyond the influence of sunlight. Speculative models consider exotic compositions or the presence of dark matter cores, granting them stability in the vast void. Some could act as seeds for planet formation if captured by new stars or collide with protoplanetary disks, injecting material and altering evolution. From an astrobiological perspective, they expand the possibilities for life beyond conventional systems. Life could exist in oceans beneath ice or sustained by geothermal or chemical energy. Every discovery strengthens our understanding that the galaxy is far more dynamic and populated than previously imagined. Rogue planets remind us that the universe is not static, that planetary systems evolve, and that extreme environments may host life. They connect planetary science, stellar dynamics, and the search for extraterrestrial life in a single continuous narrative. Even in darkness, isolated worlds move with purpose, tracing orbits defined by the invisible architecture of gravity and the chaotic past. Oh, their former systems, rogue planets, symbolize freedom and mystery. They wander without constraint, yet influence the cosmos profoundly. The study of these worlds is ongoing, and as observational methods improve, the hidden population will be revealed, bringing new insights into planetary formation, survival, and the potential for life without a sun. In the vast Milky Way, these silent travelers continue their journey, a testament to the complexity and richness of the cosmos, where even in darkness, possibilities for life persist and mysteries wait discovery. Rogue planets remain one of the most intriguing and overlooked populations in our galaxy, a reminder that the universe holds wonders beyond the familiar, that the search for life and understanding must extend beyond the light of stars. They teach us that isolation does not mean insignificance, that the galaxy is alive with hidden travelers shaping the cosmic story in ways we are only beginning to perceive. Werewolf pulsars, neutron stars that defy expectations, emitting radiation that shifts unpredictably in frequency, intensity, and form. Some pulsars suddenly change their pulse pattern, as if their internal structure rearranges itself. Without warning, the emission may speed up or slow down. Pulses become irregular or double in amplitude, then return to a normal rhythm, leaving astronomers puzzled. One possible explanation is internal phase transitions within the super-dense neutron matter. The core of the pulsar may undergo sudden rearrangements where neutrons shift or exotic quark matter forms, altering the star's rotational and magnetic properties. Magnetars, pulsars with extreme magnetic fields, often exhibit this behavior. The field lines, twisted beyond comprehension, interact with the crust and plasma surrounding the star, causing sudden bursts or lulls in emission. Some pulsars show mode switching, where radio and X-ray pulses alternate between multiple states, as if the star possesses multiple personalities, each with its own rhythm. Theoretical models suggest that the neutron star interior is layered like an onion, with a crust, mantle, and core, and sudden slippage or cracking can redistribute angular momentum, changing pulse patterns. Observations have recorded pulsars switching type from a normal radio emitter to intermittent or even nulling for hours, then resuming as if nothing happened. Magnetohydrodynamic simulations show that intense magnetic stress can fracture the crust or twist field lines, creating instabilities in emission. These unpredictable pulsars challenge our understanding of neutron star interiors and their coupling with the magnetosphere. They also provide clues to the properties of matter under extreme pressure, beyond what can be recreated. In laboratories on Earth, werewolf pulsars are not just theoretical curiosities. They have been observed in several cases, revealing that neutron stars can evolve dynamically even after millions of years of rotation. Some changes occur over milliseconds, others over years, suggesting a spectrum of underlying mechanisms. The presence of sudden glitches or anti-glitches adds further complexity. Sometimes the star spins faster, sometimes slower, without apparent cause. In all cases, the electromagnetic signature carries information about the exotic states inside the star and the interaction between matter and magnetic fields. Each observation pushes theoretical physics toward new horizons, suggesting that neutron matter may be far stranger than current models predict. The space around werewolf pulsars is far from calm. Magnetic fields, twisted by immense internal forces, extend far beyond the star itself, creating a chaotic environment. Plasma trapped in the magnetosphere spirals along field lines, accelerated to near light speeds, emitting synchrotron radiation and sometimes X-rays in unpredictable bursts. Vortices of charged particles form around these stars, creating localized regions of intense radiation pressure, distorting nearby orbits and influencing the motion of companion bodies. Present werewolf pulsars can generate winds of particles that strip atmospheres from planets or moons, passing too close, exposing surfaces to extreme radiation, or heating planetary interiors through energetic bombardment. Hypothetically, some regions near the pulsar experience relativistic particle jets capable of accelerating ions to energies normally only found in supernova remnants. The magnetic environment around these pulsars can twist and distort interstellar plasma, producing radio anomalies or localized bursts of high-energy photons. Nearby star systems may feel subtle gravitational effects from the pulsar's rotational changes or sudden glitches, altering orbital velocities and potentially destabilizing planetary systems. The interaction with the interstellar medium leads to formation of shock fronts and bow shocks, where high-energy particles collide with gas, generating observable emission lines that act as fingerprints of the pulsar's activity. Pulsar winds and magnetic turbulence may also catalyze chemical reactions in nearby clouds, creating complex molecules even in regions far from stars. In theoretical scenarios, plasma accelerated by a werewolf pulsar could reach superluminal phase velocities, appearing to move faster than light, in accordance with relativistic effects, though information transmission remains subliminal. The unpredictable emission can affect radio and X-ray observations, making pulsars appear to switch types or vanish temporarily before resuming activity. The surrounding magnetosphere is a laboratory for studying physics under extreme conditions, unreplicable on Earth, where matter and magnetic fields interact in regimes of enormous density and rapid rotation. Even distant cosmic rays can be traced back to such pulsars, showing their influence extends far beyond the immediate vicinity, impacting interstellar chemistry and galactic particle populations. In essence, werewolf pulsars reshape the space around them through energy, magnetism, and dynamic radiation, making them agents of change in their local cosmic neighborhoods. The consequences range from subtle perturbations to dramatic disruptions, potentially influencing the evolution of any nearby planetary systems or star clusters over millions of years. Their study offers insight into the interaction between neutron star interiors and the cosmos, revealing the feedback loop between extreme physics and interstellar environments. The root of a werewolf pulsar's unpredictable behavior may lie deep within the super-dense neutron matter. At its core, phase transitions in the nuclear or quark layers could rearrange the internal structure, suddenly shifting the rotation and magnetic configuration. Some theorists suggest that external influences play a role. Streams of interstellar particles or nearby objects interacting gravitationally can trigger instabilities. Exotic matter or dark matter interactions remain speculative, but could explain abrupt changes in spin rate or emission mode without visible cause. Werewolf pulsars may be undergoing cycles of energy storage and release. They're magnetic fields, analogous to solar flares, but magnitudes higher and far less predictable. The crust of a neutron star is not solid in the conventional sense. It can crack, shift, or twist under stress, transmitting changes through the magnetosphere, affecting radiation output, glitches, anti-glitches, and mode switching all contribute to a pulsar's dual identity and apparent erratic behavior. In extreme scenarios, pulsars could interact with hypothetical dark sectors or extra-dimensional fields, introducing forces beyond the standard model, temporarily altering emission characteristics. Werewolf pulsars serve as natural laboratories, testing physics under conditions unachievable on Earth, probing matter at nuclear densities and magnetic fields trillions of times stronger than any generated artificially. The impact on surrounding space remains profound, from plasma dynamics to potential disruption of nearby orbits and radiation environments. Every observation reveals the hidden complexity of neutron stars and challenges conventional models, forcing theorists to consider new physics and unseen cosmic interactions. The unpredictability is not random, but a signal of underlying mechanisms. We are only beginning to understand. Werewolf pulsars highlight the delicate balance between matter, magnetism, and extreme density, where small changes can have outsized consequences on observable behavior. Their study bridges astrophysics, nuclear physics, and cosmology, linking the interior dynamics of neutron stars with galactic scale processes. They remind us that the universe is not static, nor always predictable, even in the remnants of stellar explosions. Every pulse, every glitch is a window into the most extreme and exotic states of matter and energy existing in our galaxy. As our instruments improve, we will map the behaviors, frequencies, and spatial distribution. These werewolf pulsars, understanding their role in cosmic evolution. Ultimately, they exemplify the hidden complexity of neutron stars and the extraordinary possibilities present in the extreme universe. Werewolf pulsars remain one of the most enigmatic and scientifically rich populations of stars, pushing the boundaries of what we know. and what we imagine about the cosmos